Alright, welcome to the Power Factor AR tutorial. This video will go over how to spot if the Power Factor AR is valid for the facility you're looking at, how Power Factor works, what it is, and how to do the calculations. Alright, luckily Power Factor is probably the easiest AR to spot. All you need to do is look at their utility data. So you can usually get an idea of if this is going to be a successful AR or not before even getting to the facility itself. So the IAC will request from every facility it visits a year's worth of utility data. This means stuff like the electric bill, the gas bill, sometimes water, sometimes other things. If you look on the utility bills and see anything in the electric bill about power factor adjustment, or anything like that, then that means that you've got the potential for a power factor AR, and every power factor AR that I've ever seen has been a successful one, so kind of a no-brainer. I also want to pull attention to this UU0 number and name in the corner. This is the ID of a completed report and the name of somebody that worked on it. These are sort of like citations for these images that I pulled. These are real bills, real data from assessments that we've had in the past. And if you look up this ID on Box, you'll be able to find the actual report that it's from if you want more context. So probably the most complicated part about power factor is understanding why it's a problem in the first place. Essentially, all electricity delivered by the power company to any of your appliances, even in your own home, has three pieces to it. It has the total actual power that they are sending out, called kVA. It has the power that your machine is able to use, which you've probably heard of before, called kW. And then it has some leftover power called kVAR, VAR. You'll often see it referred to as with this beer analogy. The kVAR is the useless foam on the top of the beer that you actually want to use. A little more precise diagram of what's happening are these two alternating currents and the lag between them. To put it simply, you want these sine waves to overlap as much as possible. Right now there's a big gap between them and it's creating destructive interference, and that just means that you're going to have more kVAR than kW. When that happens, that means that you're wasting more power and you have to pay for more from the actual power company. If you want to look into it more, look into AC power and power phasing and how lag works between waves. But for now, I'm just going to leave it at this. As far as what we actually recommend to the facility and what saves them money, as long as they have a power factor of at least 0.9 or more, they will not receive charges from their power company. This means that they're using 90% of the power that's delivered as actual working power for their appliances and machines. To change the phase of the incoming power, in other words, to improve their power factor, they just need to install some capacitors. We'll go over how to calculate the size and cost of those capacitors later. We're going to hold off on sizing the capacitor for just a second to find the savings. This is how we typically do things. We calculate the savings first and then the implementation cost. And we do that, this is the order that we do things in the write-up as well. So savings are pretty simple. You'll go through their utility bills and get the amount of kW per month that they had to adjust by and total that up and multiply it by the kilowatt rate for that facility, which hopefully you either remember or can find from the utility analysis, or you can just ask somebody else on your team. While you're looking through the utility bills, keep a list and get an average of all of the adjustment kilowatts and the power factor for each month, as these will be needed for implementation cost soon. In this case, the kW rate from the utility bills was $15.60. Again, this is real data, and we'll use this real number in the calculations on the next slide. So now we actually need to size the capacitor. We know that we have a power factor of 0.836 from the data we gathered on the last slide, and we want to get it up to a power factor of 0.9 or more. To do this, we will use this as our main equation. The reactive kVAR is going to be the size of capacitor that we'll want to buy, or that we will want to recommend that they buy. We already have the average adjustment kilowatts from the last slide. In our case, it's 222. You can see that on the table on the right. So we just need to find the CCF constant. This requires having our current and goal power factor. So you can get its value from a standards table. I have a link here if you want to find this video on Box, or you can just Google it, or you can calculate it by hand using this equation. You can see that they result in essentially the same number, and for those interested, this figure shows the beer analogy again and kind of hints at the trigonometric reason why this equation works. In general, this website, theengineeringmindset.com, very good for what we do. I highly recommend that you go check out the video that I took this photo from and their website for your future questions. Anyway, we get a CCF value of 0.18. So we just finish that equation, plug the things in, and get the reactive kVAR, aka the minimum capacitance that we need for our capacitor to be able to handle. Now, they don't actually sell 860 kVAR capacitors. You'd have to get it custom made or something. So just round up and do your best. What happened in this particular report was the person recommended two 450 kVAR capacitors, or 900 kVAR total. Make sure you round up. Don't round down. We don't want to undersize it and have one of the capacitors explode. But round up, find the best fit that you can, and get as many quotes for the price as possible. Here are two websites you can look at where you can get quotes or just do your best approximate pricing. I'm saying it over and over, but getting quotes is the best way to be accurate, makes us look very official, and is just great practice. But if you can't do them, or the company doesn't get back to you for whatever reason, you can sort of prorate your own capacitor cost as long as you provide enough evidence. So typically what we would do is get the savings, get the cost, and then apply any incentives that work for the AR. Incentives are things like rewards from the government or the power company or some other large organization that help cover the cost of a project for being maybe environmentally friendly or reducing the load on the power grid, things like that. Power factor does not have any incentives, so you can just ignore that part for this specific AR. This equation here is the only equation that is used in every write-up and every AR calculation. It's simply cost over savings. Since you don't have incentives, you can ignore that part. Cost over savings equals the payback period, aka how long it takes for the facility to make the money back that they spent on doing this recommendation that we've given them. Typically, since power factor is cheap and easy to manage. This will be under 1 year. If it's not under 1 year, it should be under 2. But the IAC policy is as long as it's under 5 years of payback, then it's worth recommending. I've never seen a power factor AR get turned down for having too high of a payback period. So get this number and you can move on to your write-up now that all your calculations are done. And doing the write-up is an entire other topic. I've made a separate video for it. It should be at the end of the playlist that you're watching this video on.